Late 2024. Satellite imagery begins showing something unusual. Rail yards once operating at near constant capacity are suddenly idle. Long rows of armored vehicles appear, unchanged, week after week. Drone launch sites that were active just days earlier go silent. At first, these signals seem disconnected. A logistics bottleneck here, a factory slowdown there, a temporary communications outage. But then the pattern emerges. Across multiple regions, critical military systems are no longer synchronizing. Supply is no longer matching demand. Repair cycles are falling behind operational tempo. Reconnaissance coverage is thinning at precisely the wrong moment. This isn't a battlefield defeat. There is no single strike to point to. This is something more dangerous, a structural failure inside the machinery that sustains modern warfare. And once systems begin failing at this level, they are not easily stopped. The first warnings did not come from the battlefield. They came from space. In mid-October 2024, commercial satellite providers captured a series of images that immediately drew the attention of OSINT analysts. Key rail junctions feeding southern operational sectors showed a sharp decline in rolling stock movement. Normally, these yards operate on predictable rhythms: inbound munitions, outbound fuel, rotational equipment transfers. But the pattern had changed. Rail cars were present, but stationary. Loading zones appeared congested, yet inactive. Auxiliary tracks showed signs of backlog rather than throughput. At the same time, analysts monitoring industrial facilities noticed irregular production signatures. Thermal data from known drone assembly and refurbishment sites showed reduced activity cycles, not shutdowns, but interruptions. Start-stop behavior inconsistent with stable manufacturing output. Individually, none of this was decisive. Modern militaries experience friction constantly. Delays happen, systems flex. But modern warfare depends on synchronization. When logistics, production, and reconnaissance fall out of alignment, even briefly, the effects multiply. Signals intelligence added another layer. Intercepted logistics reports referenced temporary redistribution measures, a phrase often used to mask shortfalls rather than surpluses. Regional documents, later leaked, indicated that several reserve formations failed to meet scheduled readiness checkpoints, not due to personnel gaps, but missing equipment allocations. This distinction mattered. Personnel can be reassigned. Equipment shortfalls cascade. By late November, frontline commanders were reporting mismatches between requested support packages and delivered quantities. Not total absence, but inconsistent fulfillment. Artillery units received fewer shells than projected. Armored elements extended maintenance intervals beyond standard tolerances. Drone operators reported gaps in coverage windows once considered continuous. None of this appeared catastrophic, yet. But to analysts familiar with sustainment warfare, the picture was clear. Russia was no longer operating at equilibrium. The system was compensating, and compensation is never permanent. By the time these indicators became visible across multiple domains, the question was no longer whether something had broken. It was how far the fracture would spread, and whether Moscow still had the capacity to stop it. Modern warfare does not move on roads. It moves on rails. For Russia, rail infrastructure is not a support system. It is the backbone of operational sustainment. Fuel, ammunition, armored vehicles, repair components, and personnel rotations all depend on a tightly synchronized rail network. By late 2024, that synchronization was breaking down. OSINT analysts tracking rail traffic through commercial satellite imagery noticed an unusual anomaly: density without motion. Rail yards feeding southern operational sectors were full, but not flowing. Flat cars loaded with containers remained stationary for days. Switching yards showed congestion patterns inconsistent with scheduled throughput. This was not damage. This was overload. For weeks, these nodes had been operating beyond design capacity. Civilian freight traffic had been redirected to military corridors. Rolling stock cycles shortened. Maintenance windows compressed. At a certain point, systems don't fail dramatically. They stall. Internal logistics documents, later partially leaked, referenced a temporary redistribution of rolling assets. In military logistics language, that phrase often signals a shortfall being masked by reallocation. But reallocation only works when there is slack in the system. There wasn't. Railway signaling delays began compounding. Maintenance crews were stretched thin. Minor mechanical issues accumulated faster than they could be cleared. The result was a cascading slowdown. Units further down the line did not stop receiving supplies entirely, but deliveries became irregular. Predictability vanished. And in modern warfare, unpredictability is operational friction. Artillery planners rely on consistent resupply curves. Armored units schedule maintenance cycles around known transport windows. Drone units depend on battery shipments, spare airframes, and electronic components arriving on time. When rail throughput falters, every downstream system compensates until it can't. This bottleneck also exposed a deeper structural vulnerability. Russia's military rail network is optimized for volume, not flexibility. It excels at moving large quantities along predefined corridors. It struggles when forced to reroute dynamically under sustained load. Once a critical junction slowed, alternative routes absorbed the pressure, briefly. Then they began exhibiting the same symptoms. This was not sabotage, not an external strike. It was systemic saturation. By early December, operational commanders were no longer asking when supplies would arrive. They were asking whether delivery schedules still meant anything at all. And as rail reliability declined, the strain shifted elsewhere. To the systems that depend on timing more than mass. The drones. Modern warfare sees before it moves. And in late 2024, Russia's ability to see began to narrow. The first signs did not come from the front lines. They came from absence. OSINT analysts tracking known Russian reconnaissance patterns noticed expanding gaps in aerial coverage across multiple sectors. Flight paths that had appeared daily, sometimes hourly, simply stopped repeating. Not everywhere, not all at once, but enough to raise alarms. Russia's unmanned aerial systems form a layered reconnaissance ecosystem. Short-range quadcopters for immediate situational awareness. Fixed-wing drones for deeper observation. Electronic relay platforms linking forward units to rear command nodes. This system depends on three things: continuous production, rapid repair, and reliable component flow. By November, all three were under strain. Satellite imagery of drone production and refurbishment facilities revealed inconsistent operational signatures. Thermal patterns fluctuated. Power usage dropped, then spiked, then dropped again. This was not a clean shutdown. It was instability. Open-source procurement data showed delays in key components: optics, flight controllers, encrypted communications modules. Many of these rely on complex supply chains, some domestic, some external. When even one link slows, assembly lines stall. Internal reports later referenced temporary output adjustments, a phrase that sounds controlled, but rarely is. At the same time, field units reported rising drone attrition rates, not from engagement, but from mechanical fatigue. Airframes exceeded expected flight hours. Battery cycles shortened. Navigation errors increased. Normally, such losses are offset by replacement, but replacements were not arriving at the expected rate. As drone availability declined, commanders adapted. Launch windows were shortened. Coverage zones were prioritized. Redundancy disappeared. Where continuous observation once existed, there were now intervals of uncertainty. This had second-order effects. Artillery coordination relies on timely target verification. Electronic warfare units depend on drone-borne sensors to cue emissions. Commanders use aerial feeds to validate assumptions made hours earlier. When those feeds falter, decision-making slows, not because commanders hesitate, but because confirmation is missing. Russia's drone ecosystem was not destroyed. It was degraded, and degradation is harder to reverse than loss. Factories can be rebuilt. Systems can be replaced. But restoring tempo, once it is lost, requires resources the system was already struggling to provide. By December, analysts began describing the situation with a specific term: reconnaissance elasticity collapse. The system still functioned, but it could no longer stretch, and as visibility narrowed, another pressure point began to surface, one that could not be compensated for with prioritization alone. Ammunition. In modern warfare, firepower is not defined by volume alone. It is defined by rhythm. Ammunition systems are designed around predictable consumption curves. Production, storage, transport, and allocation all depend on timing, not just quantity. By late 2024, that rhythm inside Russia's military system was breaking down. The first indicators appeared in internal logistics summaries. Requests submitted by operational units were no longer matched by standardized delivery schedules. Instead, reports referenced partial fulfillment and adjusted allocations. On paper, ammunition output still existed. Factories continued operating. Warehouses were not empty, but the flow between them had become uneven. OSINT analysts monitoring industrial facilities noticed irregular production cycles at multiple ammunition plants. Thermal signatures suggested batch-based manufacturing rather than continuous output. Energy consumption fluctuated in patterns inconsistent with steady-state production. This pointed to a critical constraint: input instability. Explosives, propellants, precision-machined casings, and fuses require synchronized supply chains. Disruptions in any one category force entire lines to pause or slow. Rail bottlenecks compounded the problem. Even when ammunition was produced, moving it forward became unpredictable. As a result, field units experienced variability rather than absence. Some resupply convoys arrived close to schedule. Others were delayed without clear explanation. For planners, this was worse than shortage. Artillery coordination relies on known availability windows. Fire planning models assume consistent resupply intervals to support sustained operations. When deliveries become irregular, commanders are forced to adapt. Requests were revised downward, not because demand decreased, but because confidence did. Units planned around minimum guaranteed delivery rather than projected need. This had cascading effects. Operational tempo slowed, not from external pressure, but from internal uncertainty. Assets remained available, but were used more cautiously. Synchronization between reconnaissance, fires, and maneuver became harder to maintain. Internal communications reflected growing concern. One leaked memo referenced increasing deviation between planned and executed fire schedules. Another cited extended reliance on legacy stockpiles due to delayed replenishment. Legacy stockpiles, by definition, are finite and unevenly distributed. As newer production struggled to re-establish rhythm, older inventories filled the gap. But those inventories were never designed for prolonged high-intensity use. Packaging standards differed. Storage conditions varied. Compatibility issues emerged with newer systems. Each workaround solved a short-term problem, while creating long-term inefficiency. Attempts to centralize distribution only increased pressure on already strained logistics nodes. Decentralization improved flexibility, but reduced oversight. There was no optimal solution. By December, analysts began describing the situation not as an ammunition shortage, but as an ammunition coherence problem. The system still had mass. It still had capacity. What it lacked was alignment. And as ammunition rhythm faltered, another critical system reached its limit: the ability to repair and return equipment to service. Modern warfare does not end when equipment is damaged. It ends when equipment cannot return. By late 2024, Russia's repair and refurbishment system was under visible strain, and unlike ammunition or drones, this problem could not be offset with prioritization alone. Repair capacity is governed by three hard limits: skilled labor, spare parts, and time. All three were converging toward failure. OSINT analysts examining vehicle depots and industrial repair facilities began noticing a troubling pattern. Large concentrations of armored vehicles remained stationary for extended periods. Thermal signatures showed minimal workshop activity compared to previous cycles. Movement in and out of depots slowed, even as demand increased. This was not a lack of equipment. It was a lack of throughput. Modern armored platforms rely on modular repair systems: power packs, optics, electronics, fire control units. These systems are designed for rapid swap-out, not field improvisation. But by November, internal documents referenced extended refurbishment timelines and non-standard component substitution. In practical terms, this meant repair crews were waiting for electronics, waiting for precision-machined parts, waiting for subsystems that no longer arrived on schedule. Rail bottlenecks delayed heavy components. Ammunition factories competed for skilled labor. Drone production absorbed electronic supply chains that armor repair also depended on. The system was cannibalizing itself. Field units adapted the only way they could. Maintenance intervals were extended. Minor faults were deferred. Vehicles operated beyond recommended service limits. These measures preserved short-term availability, but degraded long-term reliability. Internal assessments began referencing fleet degradation acceleration, a technical phrase that signals a critical shift: more systems leaving service than returning to it. Unlike losses, repair backlog accumulates invisibly. Each delayed vehicle occupies space, consumes manpower, blocks workflow. And as depots filled, turnaround times increased even further. Attempts to decentralize repairs provided limited relief. Field-level fixes restored partial functionality, but could not address deeper mechanical or electronic issues. Meanwhile, factories tasked with deep overhaul faced their own constraints. Overworked personnel, equipment operating continuously without downtime. Quality control cycles compressed to meet quotas. The result was not collapse, but brittleness. A system still operating, but with no margin left. By December, analysts observed a critical shift. Repair timelines were no longer predictable. Commanders could not plan rotations. Units could not forecast availability. Operational planners began assuming that damaged equipment would not return on schedule, if at all. This assumption changed behavior. Assets were used more cautiously. Exposure was minimized. Operational ambition narrowed. Not because capability was gone, but because sustainment could no longer be trusted. And as repair capacity faltered, the pressure moved upward into the personnel system tasked with filling the gaps. Mobilization. Mobilization looks decisive on paper. Schedules are issued. Targets are set. Units are declared ready. But modern warfare does not measure readiness by headcount alone. It measures it by integration. By late 2024, Russia's mobilization system was under growing strain, not because of numbers, but because the system surrounding those numbers could no longer keep pace. Internal regional documents, later leaked, revealed a recurring issue. Mobilization units were forming, but missing key components, not personnel, equipment. Vehicles arrived late, or not at all. Communications gear was incomplete. Electronic systems required to integrate units into higher command networks were delayed. This created a structural mismatch. Mobilized formations existed administratively, but not operationally. Training cycles were compressed to meet deadlines. Equipment familiarization was reduced. Units were declared ready with caveats attached, caveats that accumulated quietly. From a systems perspective, this mattered. Modern formations rely on interoperability. Radios must link with command nodes. Digital mapping systems must sync with reconnaissance feeds. Logistics elements must integrate seamlessly into supply chains already under strain. When even one of these links fails, readiness becomes conditional. OSINT analysts monitoring training areas noticed unusual patterns. Equipment concentrations remained static longer than expected. Live system exercises were limited in scope. Movement signatures suggested administrative readiness rather than full operational deployment. At the same time, internal correspondence referenced adjusted readiness criteria, a bureaucratic phrase that often signals standards being lowered to meet timelines. This was not deception. It was necessity. As repair capacity declined and equipment availability tightened, mobilization planners faced an impossible equation: delay formation and risk strategic gaps. Deploy early and accept reduced effectiveness. The choice was made repeatedly. Mobilization timelines were met, but at the cost of cohesion. Units entered the system with incomplete logistics support. Some lacked organic repair assets. Others depended on external supply channels already operating beyond capacity. This shifted pressure upward. Higher-level commands were forced to compensate, reassigning assets, redistributing equipment, adjusting operational expectations. But compensation has limits. As more mobilized units entered service, they did not reinforce the system. They consumed it. Each additional formation increased demand for ammunition, repairs, transport, and command bandwidth. The system absorbed this, briefly. Then strain became visible. Analysts began describing the situation with a precise term: mobilization dilution. The appearance of scale remained. The substance did not keep pace. And as mobilization stress compounded existing failures, the focus shifted to the center, where decisions were being made to stabilize a system already operating at its limits. The Kremlin. When complex systems begin to fail, leadership responds instinctively. Centralize control, issue directives, accelerate output. In late 2024, the Kremlin did all three. Emergency coordination meetings were convened across defense, transport, and industrial ministries. Production targets were revised upward. Logistics priorities were reordered. On paper, the response was decisive. In practice, it revealed the core limitation of centralized crisis management. Control does not create capacity. Rail authorities were instructed to prioritize military traffic, but rail networks already operating at saturation could not increase throughput without reducing safety margins or maintenance windows. Factories were ordered to extend shifts, but labor pools were finite. Machinery already running near continuous duty could not accelerate without increasing fault rates. Repair depots were told to shorten refurbishment timelines. But missing components do not appear faster because deadlines change. Each directive created movement, but not resolution. OSINT analysts tracking industrial activity noticed a telling pattern. Output spikes were followed by sharp declines. Facilities surged briefly, then fell back below baseline. This oscillation is a classic sign of system fatigue. Rather than stabilizing production, pressure amplified volatility. Internal communications hinted at growing coordination friction. Transport schedules changed faster than units could adapt. Priority designations overlapped, diluting their meaning. What emerged was not a linear recovery, but a feedback loop. Each intervention exposed another constraint. Increase ammunition output and rail congestion worsened. Accelerate repairs, and component shortages deepened. Expand mobilization, and sustainment demand spiked. The system was no longer failing quietly, it was failing visibly. By December, analysts began noting a shift in messaging. Public statements emphasized resilience and adaptation rather than expansion. Operational language pivoted from growth to endurance. This shift mattered. It signaled an implicit recognition that the system could not be rapidly fixed, only managed. Strategic objectives were adjusted accordingly. Operations became more selective. Resource-intensive actions were spaced further apart. Risk tolerance narrowed. These were not signs of collapse. They were signs of constraint acknowledgement. And constraints, once acknowledged, shape strategy. The Kremlin's challenge was no longer restoring full capability. It was preventing further degradation. But systems operating without margin have a problem. They cannot absorb shock. And as winter deepened, analysts began asking a harder question, not about intent or resolve or control, but about sustainability. Modern wars are not decided by single moments. They are decided by systems under pressure. By the end of 2024, analysts no longer debated whether something inside Russia's military structure had failed. That question was settled. The real question became more consequential. Can the system recover fast enough to matter? From a technical standpoint, the answer depends on three variables. First, time. Industrial systems can adapt, but not instantly. Rail networks require maintenance cycles to restore reliability. Factories need downtime to stabilize output. Repair pipelines must clear backlogs before tempo can increase again. None of these processes operate on political timelines. Second, inputs. Ammunition, electronics, optics, propulsion systems, and communications hardware all depend on layered supply chains. Many of those chains were already optimized for peacetime efficiency, not sustained high-intensity demand. Rebuilding elasticity requires diversification, redundancy, and margin. All three take time and resources already under strain. Third, coordination bandwidth. As systems degrade, command complexity increases. Decision-makers are forced to manage exceptions rather than norms. Every deviation consumes attention. Eventually, leadership shifts from planning forward to preventing collapse. OSINT indicators suggest that Russia entered this phase in late 2024. Not retreat, not defeat, but constraint-driven strategy. Operations became more selective. Sustainment took precedence over expansion. Risk management replaced tempo dominance. This does not mean capability disappeared. It means choices narrowed. In modern warfare, narrowing choices is decisive. It limits initiative, reduces flexibility, forces predictability. And predictability is exploitable, not necessarily by force, but by time. The deeper implication extends beyond this conflict. What unfolded in late 2024 illustrates a broader truth about modern military power. Industrial scale alone is not enough, nor is technological sophistication. Sustained warfare demands alignment between logistics, production, repair, reconnaissance, and command. When alignment breaks, systems do not fail dramatically. They erode, quietly, incrementally, relentlessly. Russia's challenge moving forward is not restoring strength overnight. It is rebuilding coherence while remaining operational. That is the hardest task any military can face, because it must be done under pressure, with no pause and no reset. And once a system begins operating without margin, every additional strain carries disproportionate risk. This is what broke. Not a weapon, not a unit, not a front line, but the sustainment architecture of modern warfare. And until that architecture regains balance, no amount of orders, no single leader can simply command it back into place.